So let's just get started. So as I introduced many times, so I'm Yishan. I'm a PhD student at the Department of Physics. So I joined Purdue in January 2021. So our group is hosting this weekly quantum seminar as a quantum educational program. So this quantum educational program is funded by Department of Defense. So it started from last September. So this kind of program will last for 3 years. So we host this kind of quantum seminar are part of that quantum education program. And also this quantum seminar also partially supported by Purdue Quantum Science Engineering Institute. So some of the pieces they also provide some funding. So today is our first seminar. So it's my great honor to introduce this week's speaker, Alexandria Moore. She's a doctoral student in electrical engineering at Purdue University, advised by Professor Andrew Weiner. Her primary focus is in quantum optics. Her research includes implementing quantum algorithms using high-dimensional photonic systems and developing algorithms which leverage the advantages for high-dimensional photonic qubits. She also works on high-dimensional entanglement certification approaches. So let's welcome her to give us a talk.
Hello, and as you just heard, I am Alexandria Moore. Today we're going to be going over quantum states, and we're going to be doing it hopefully through the lens primarily of photonics and of high-dimensional systems. We will, however, see this language be hopefully very broadly applicable to almost any quantum system that you see, but I find it more helpful to go at things through concrete examples and then abstract them out. So kind of the first half of the talk is going to be giving outline to make sure that everything in the latter part is clear to anyone with any level of background in quantum. So first we're going to introduce quantum states through polarized photons, and then we're going to talk about quantum circuit notation. We're going to talk about the value of entanglement, both in computation and in networking and quantum communications. And then we'll move on to talking about 3 big ways that people are interested in studying quantum states. This is through Bell state analysis, through quantum state tomography, and through entanglement certification. All right, so as the intro, consider that we have linearly polarized light. Light is an electromagnetic wave, and as it propagates in any given direction, the electric field points somewhere. If it points the same direction the entire time it's propagating, it is called linearly polarized light. The electric field could be pointed up, pointed to the side, pointed down, whatever. In the most general sense, we talk about light as being elliptically polarized. So your electric field can rotate as it propagates. But imagine that we do have a linearly polarized light at some angle with respect to the horizontal. There are a few different ways that we can talk about it. We can talk about it in terms of its horizontal and vertical components. So this is a vector. We can break it down into 2 orthogonal components. The horizontal will just represent as this vector, the 1, 0 vector. The vertical will represent as a vector, the 0, 1 vector. And then their magnitudes are cosine theta, sine theta, like you'd expect. And so you can represent this state in the horizontal vertical basis with this vector, cosine theta, sine theta in the HV basis. If you want to be a little bit more general about it and a little bit more flexible, you can just represent these vectors with cats. So this is the horizontal state represented by the horizontal vector. Whenever you see notation like this, you can imagine it as a column vector, whatever dimensionality your system is in. All right, plus, of course, the vertical vector like that. You're going to see the exact same story for diagonal, anti-diagonal. There's nothing that's particularly great about horizontal, vertical. You can also choose diagonal, anti-diagonal axes, and you can do the exact same thing. So in the diag, anti-diag basis, you have the 0, 1 vector, 1, 0 vector, but in this case, 1, 0 represents diag, 0, 1 represents anti-diagonal. All right, and getting a little bit more abstract, you can even write linearly polarized light in terms of the right and left circular basis. So in this case, our column vector 1, 0 is now representing the right circular state. 0, 1 now represents your left circular state. But in order to project a linear light onto the right and left circular, you do end up picking up a phase. But this is important to note because quantum states don't have to have just real values in front of them. They can be complex. So all three of these states are equally great ways of representing this one particular state of polarized light. And so since we have all these great ways of talking about light, how do we choose which one we're going to use? Generally, people stick with the basis that they're going to end up measuring in. So for instance, this is my linearly polarized light at angle theta. We can represent it in the HV basis, but we can equally well represent it in the anti-diagonal basis. So what does that mean? If I take this linearly polarized light and I send it through a vertical polarizer, it's not always going to pass through the polarizer, okay? It passes through with some success probability, depending on its orientation. If the light is entirely vertical, it's going to always pass through the polarizer. If it's entirely horizontal, it will never pass through. The way we talk about this for a single photon quantum state is that its probability of passing through this vertical slit and then getting detected is probability of detection given a vertical polarizer. You can represent this by taking the vertical polarizer, treating it now as, this is called a bra. This is bra-ket notation. Those kets from the last slide represent column vectors. These bras are the conjugate transpose of their corresponding kets. So if you have a bra-ket, you have a scalar product, you have a number, could be complex. So probability of being detected in vertical, well, probability of going through the vertical if you're horizontally polarized is 0. Probability of going through vertical if you're vertically polarized is 1. You take the magnitude squared to actually end up with a probability. And so probability of successfully passing through here is sine squared. And that's really easy to see if you had written this state in the HV basis. But if you're dealing with a diagonal polarizer followed by a detector, it's not so easy to see if you just look at your HV basis. Instead, you'd rather use your DA basis. All right, because then it's really easy to see the exact same logic goes on. Probability of going through diagonal if you're in the diagonal state, 1. Probability of diagonal if you're anti-diagonal, 0. Here's your probability of successfully passing through for linearly polarized light. All right, and so that was just to give you an idea of what people talk about when they say things like a 0 ket and a 1 ket. Most quantum systems that people like talking about are usually 2-level. And so they can just say, well, this could be your horizontal state, this could be your vertical state, this could be your diagonal state, this could be antidiag, this could be right circular, left circular. It doesn't matter. The most general way to talk about it is just calling them 0 and 1. Depending on the system you're using, people could adopt other notations. Sometimes instead of using 0 ket and the 1 ket, people will use plus and minus ket. People will use up arrow and down arrow, especially with respect to like electron spins. But any quantum state that's 2-level can be represented like this. You can represent any state as a sum of 2, preferably orthogonal vectors. It's just a lot more convenient that way. And both of these vectors have some complex probability amplitude out in front. Since the probability of doing one of 2 mutually exclusive things, those are the only 2 things you can do, has to sum to 1. These amplitudes have to sum to 1. Okay, so remember a 0 vector is 1, 0, 1 vector is 0, 1. These properties we saw in the last slide. But something really interesting about quantum states is if you have some kind of phase out in front, and you're finding the success probability of anything, this gets a magnitude squared on it, and that magnitude squared is always 1. So there's no actual way to distinguish between this state and this state. And so they're considered to be equivalent states. You can write this or you can write this, and they're considered by anyone to be entirely identical because they have just a difference of a global phase factor. And so for this reason, I find a better way to write these states instead of doing complex A plus complex B is to think about one complex value, which I'm going to call alpha, and then just multiply your state, whatever it is, by a global phase, such that this quantity always is a perfectly real number. So now this is a totally real number. This has some magnitude less or equal to 1, and it also represents the phase, the relative phase between the 0 state and the 1 state. Okay, remember that these phases do matter. For example, if I have a real number here and a real number here, this represents linearly polarized light in some direction. However, once you have a phase here, if I have a real number here and a complex value here, that would represent elliptically polarized light. Okay, so these phases do have meanings in polarization, and they do have meanings no matter what basis you're working in. Okay, And so we want to talk now about circuit notation and also start bringing in more photons into our conversation. So for instance, this is psi A, it represents photon A. This is psi B, it represents photon B. What we have here is a set of single photon gates. So photon A is being operated by U1, U2, U3. Whenever you see gates like this in circuit notation, they're unitaries, which means that they multiply by their inverse is the identity matrix. They have to have this property in order to conserve probability. Your probability is always going to be 1. You can't have this state have a probability of being measured in either of the stages as being 1 and then end up with something larger than that. They're also unitaries because they have to be reversible. If your state is reversible, you usually wouldn't use this kind of notation. You usually use some kind of measurement notation along with it. But in any case, this photon is being acted on by 3 gates. They could be photowave planes or something like that. And this is the final state at the output of the circuit. This photon B, is being operated on by some gate, and this is its output at the end of the circuit. So this input is considered to be separable because state A and state B have nothing to do with each other. They could have come from totally different places. They have no relation, they have no dependence. And because state A is operated upon by these 3 single photon gates, and state B is operated on by just some other single photon gate, they still have nothing to do with each other at the end of the circuit. All right, so they started in a state that we'll call separable, and they also still end in a state that's separable. All right, these input and output are separable states. That's different for multi-photon gates. When we come out to multi-photon gates, we might have 2 photons that initially have nothing to do with one another. And they might both have some single photon gates in here, but the circuit also has a gate that spans across both photons. That means what this gate does depends on the status of both photon A and photon B. That means at the end of the circuit, there is no way to separate out the gate operations on photon A from the gate operations on photon B. They are non-separable. Okay, so separable states when you have single photon gates, non-separable states with multi-photon gates. Okay, so why do we care about things being non-separable? Probably have some intuition just looking at that last picture, but we'll talk about it a little bit more. This is what separable states are written as when you want to talk about the total state of a system with multiple parties in it. For example, multiple photons in it. This is how we represent the column vectors. You take A naught, multiply it by the B vector, take A1, multiply it by the B vector. You now have 2-dimensional states that together make 1 4-dimensional system. All right, this is our separable state. We can still separate out part A from part B. As without loss of generality, we could always write photon A as in terms of alpha and photon B in terms of some complex number of beta. A separable state is fully described by 2 complex values. That's its information carrying capacity if we know that it's separable. All right, as opposed to a more general 2-photon state, potentially a non-separable state. This is our state. It has C0, C1, C2, C3. If C0 over C1 is not equal to C2 over C3, then the state is non-separable. You can't talk about photon A really without talking about photon B. And in this case, you would actually need 3 different complex values in order to describe this system. All right, so if we have, instead of just having 2 photons in these states, let's say we have n photons. Okay, if you have n photons, which are all 2 level, you're going to require n complex parameters to describe them. Okay, if you have n photons and they're in non-separable states, they can have any arrangement, you're going to find that they have 2 to the n minus 1 complex parameters to describe them. Okay, this is how we actually access the entire promised space of a quantum system. If you don't have non-separable states, you really can't do arbitrary operations, and you really don't genuinely have 4 dimensions to work with. You're limiting yourselves to the separable world. Okay, so separability and entanglement are almost always synonyms. I'm going to treat them as synonyms for the rest of this talk. So this non-separability is entanglement. Do we need it? Yes, in quantum computing. If you want to actually access the quantum advantage of quantum computing, you need multi-party gates. You need those gates that can span across multiple different parties in your system. And you also have to maintain coherence between the parties in your system. if your parties decohere, they essentially become separable and they're not that useful anymore. You can't use the entire space you want to use. So this is our quantum advantage in computational power, which comes about by entanglement. And in the next slides, we're also going to see that it's also valuable in quantum communications. We're not going to see it today, but quantum communications kind of limit the way that we would generally try to transmit classical information. We would use repeaters, we would amplify, we would do certain types of classical error correction. We don't have access to any of that in the quantum world. In the quantum world, though, you can send a quantum state from one user to another without transporting that quantum state over a communication channel. You can teleport the state from one user to another by consuming pre-prepared entangled states. So entanglement is imperative in quantum computing because it's how you access the entire computational space you want to work with. It's imperative in quantum communications because it's actually how you can transmit quantum states between various users in the network. Okay, so in the sense of networking, we usually think of entanglement as a resource, something that gets consumed, something that gets used up in order to accomplish some task. All right, but what exactly is entanglement? Two or more parties are entangled when the correlation between the pair is classical than be possible, is stronger than be possible in a classical system, which is to say it's stronger than you can have in any separable system. All right, you'll usually see this terminology a lot, LOCC. It stands for local operations and classical communications. What that really is think back to the quantum circuit. A local operation is a single photon gate. If you're only employing single photon gates and measurements, you can never increase the entanglement in a system. Having entanglement between two parties, having really strong quantum correlations, requires you to have those multi-photon gates. Okay, so entanglement, you can't generate it once your two parties are already separated. You have two photons together, you can generate entanglement, and then you can send them far apart, and they will never get any more entangled. All right, and usually when people are talking about entanglement, especially in terms of communications, you're going to see Bell states come up all the time. This is probably your most famous Bell state. When photon A is in 0, photon B is in 0. When photon A is in 1, photon B is in 1. And these relationships are coherent. Okay, the other four Bell states, or other three Bell states, are about what you think they would be. Same story, but now they have a phase of 180 degrees between them. Or when photon A is in 0, photon B is in 1, and vice versa, and also with states. These four Bell states actually do make up a basis. So if you want to describe any state, you can do it with any number of bases, but just as a note, this does form a basis to describe the system, which is part of the reason that what you're going to see now, quantum teleportation, works out the way it does. All right, so quantum teleportation, famous problem. Alice has a quantum state and she wants to send it to Bob. Okay, Alice and Bob, fortunately, have already managed to generate and share between them one Bell state. Okay, so this Bell state is a 2-photon state. It's entangled. Alice has one photon, Bob has the other photon. What Alice can do here, and this, we won't go into gates today, but this is a C0 gate. What's important to notice is that it's a 2-photon gate. All right, Alice interacts her state with the Bell state, performs another operation, and then performs 2 measurements. In quantum circuits, whenever you see these solid lines, they represent quantum states. Whenever you see these double lines, they represent classical information. So bits like 0 and 1. So we perform a measurement, and based on the results of these measurements, she sends them over any network she wants, a classical network, to Bob. And based on these results, Bob does some operations on his half of that Bell state, and then he actually ends up with Alice's initial state. Okay, this was able to be accomplished without you ever needing to transmit this state over any significant distance. Okay, so if you can manage to get these Bell states distributed throughout some kind of network between the end users, you can send quantum information from any user to any user. So the way we like to do this is with Bell state analysis. So we'll talk a little bit more about what we do with Bell state analysis on the next slide, but right now I'm just going to introduce it. What you should notice about Bell state analysis is that this gate is the exact same gate and these measurements are the exact same measurements that Alice did on the last slide. But now we're changing a little bit what the input is. So this is the ideal bell state analysis. You start with some unknown quantum state, but it's guaranteed to be in one of the 4 bell states. So as long as you know that you have one of the 4 bell states, you can use this circuit to perfectly discriminate which one you have. All right, if you have the famous 0, 0 plus 1, 1 bell state, you'll end up measuring both of these systems in 0 every time. If you have the same thing, but with the opposite phase, you'll get 1, 0, 0, 1, 1, 0 with positive phase, you get this result, and 0, 1, 1, 0 with the negative phase, you get this result. Unfortunately, and this is where it's important to distinguish between what you can do with an abstract quantum system and what you can do with a particular platform and a particular implementation, is that photonic systems, even though they're really what you're going to have to use for any communication network, they're the only things that travel long distances quickly without interacting with their environment too much, don't have the ability to implement these gates, at least not with high success. Photonic systems have a lot of difficulty implementing 2-photon or multi-photon gates. It's a challenge. Photons don't really like to talk to each other. But something you can do is use the HOM Hongo-Mendel like bunching effect in a beam splitter. So for instance, consider that these states, these bell states that are in 0 and 1 represent horizontal and vertically polarized states. Okay, if you have a bell state coming in, for instance, think about this state, you'll have the 0, 0 state coming in plus 1, 1. If these photons are both in 0, they'll both bunch. All right, if they're in the same state, they'll either both go this direction or they will both go to this direction. And if they're both in 0, horizontal, they might bunch and come up here. And then we have a polarizing beam splitter. Well, since they're both horizontal, they're both going to end up in the same detector. Okay, so anytime we have this bell state, and the same thing will happen with 1, 1, the vertical polarizations. Anytime we have this type of bell state or this type of bell state, this system doesn't do very much that's useful to us. It'll always have a double click in any one of these 4 detectors. You don't know which detector it will be. But when you have these other 2 bell states, these bell states where the photons are in opposite states, and this would require quite a bit of math to go through, and we're not going to put it on these slides. But what you will end up with in this case is both photons will always end up on the same side of the beam splitter, but because they're in opposite polarizations, one will be split this way by a PBS, the other will be split this way by the PBS. So you know you have this bell state. When you see a coincidence in these 2 detectors, or you see a coincidence in these 2 detectors. Okay, exact same state, but with the opposite phase, has a slightly different outcome. If you see a hit in detector C0, you will see a detector in not C1. So you'll see a coincidence click between this guy and this guy, or you'll see a coincidence click between these 2 detectors. So with at least 50% success probability, we're able to realize a bell state analyzer in the photonic domain. If you want to realize a general bell state analyzer in photonics, great, we would love to see it. So what does bell state analysis let us do? It lets us actually swap entanglement. If there's some kind of entanglement source that sends 1 photon to Alice and 1 photon to our swapper, and some other entanglement source that sends 1 photon to Bob, 1 photon to our swapper, if we do this bell state analysis on these 2 different photons, what we will end up with at the end of the circuit is one of the bell states. Which bell state we have will be determined by what the status of M1 and M2 are. So this lets us take entanglement between these 2 users and turn it into entanglement between, for example, these 2 users. It lets us distribute entanglement throughout a complex quantum network. So before we go on, I've been talking a lot in terms of 2 dimensions. And it'll be relevant in a second. So I want to introduce notation for higher dimensional systems. It's really not that big of a step. Okay, classically, we have binary logic, and we usually build computers based off of binary logic, but we don't have to. You could have used ternary logic in a classical computer. We generally don't, just for practical and engineering reasons. But you can do the same thing in a quantum state. Now, obviously, there are degrees of freedom like polarization, which intrinsically have two different polarizations you can be in. There's no way to add another dimension to the polarization of a photon. But with something like the photon's frequency or the photon's energy, you can have as many dimensions as you want. You can have a bunch of frequencies that are all spaced 40 gigahertz apart, and you can label them 0 to 9, 0 to 40, however many you're able to generate. Okay, so a degree of freedom, like energy in a photon, is capable of being high dimensional. So for instance, a 2-level maximally entangled state would be 0, 0 plus 1, 1. 3-level, 0, 0 plus 1, 1 plus 2, 2. D-level, as many of these as you want in a system. Okay, so I want to, in the context, we just introduced Bell state analysis and what it's good for. Now I'm just going to do a really quick presentation on one Bell state analyzer that we looked at in our lab. When you're talking about a quantum network, or really any network, you want to get as much bandwidth as you can. You have one fiber, and you can only send one bit of information in red light in a certain period of time. But if you put red light and green light and purple light, whatever you want, all on one fiber, they don't really interact with each other. And so instead of sending one bit in red light, you can send one bit in red, one bit in orange, one bit in purple, so on and so forth. You get a lot higher information carrying capacity. All right. So while we can do BSAs in photonics where we say, okay, this is frequency 0, this is frequency 1. That's my entire system is going to be made up of frequency 0 and frequency 1 and things that are in a superposition of those. Great. And then I'll do my Bell state analyzer and I'll be very happy with that. But that's not very efficient. That's not making good use of the resources that you have in fiber optic cable or even in free space. Instead, you'd like to be able to have multiple different frequencies in your system. How do you make a Bell state analyzer that can handle that? Bell state analyzers, especially the implementation I just showed you on the last slide, were dependent on the photons entering in either identical or opposite states. What if we have frequency 0 and frequency 1, and then frequency 2 and frequency 3, where we want to map frequency 2 and 3, for example, to 0 and 1, and consider those identical for the state of our BSA? There's a tool that we've developed in our lab that we've actually used in a lot of experiments quite fruitfully, which is a quantum processor, and it's just a modulator, pole shaper modulator. And this is capable of implementing almost any, within reason, gate, single photon gate in high dimensions on a photonic system. All right, so this is what you can do easily, but it's not desirable because you don't get very much bandwidth. This is what we'd like to do, and we'd like to study how well we can use a quantum frequency processor to do it. All right, so we did do some simulations and we tested, and we found that there's kind of two different ways you could imagine your system. You could imagine them where one photon is coming in a superposition of frequency -1 and frequency 1, and another photon is coming in a superposition of frequency 0 and frequency 2. We looked at what type of gate we have to implement on the quantum frequency processor, and it was a little bit demanding on the pole shaper and the modulators. What you can do instead is, all right, there's another way we could have high bandwidth in a system. We could have photon A come in a superposition of frequency -1 and frequency 0, and B come in a superposition of frequency 1 and frequency 2. All right, this is a little bit less demanding to implement on the quantum frequency processor, and so we ended up doing that, and we actually did get pretty positive results. Again, this is still a Bell state analyzer that only has the photonic limitation of 50% success probability. It's only capable of distinguishing 2 of your desired Bell states, but it does do that very well with very high fidelity. All right, and so that's Bell state analysis. It's really important for quantum networking, and these are some of the types of experiments people are doing in order to try to develop quantum networks and play with the idea and extend it into and making use along the way of systems that aren't like polarization, which are intrinsically 2-level, of systems that can be arbitrarily high dimensional. Okay. And I also want to bring up one other interesting advantage, as long as we're talking about high dimensional states, with respect to Bell state analysis. And we're not really going to go through all this math right here again, But I do want to point out that your 50% success probability isn't totally set in stone. If you're willing to start with a very high dimensional state or just a medium high dimensional state, for example, a system that's in state 1, 2, and 3, and you're trying to swap entanglement between two parties, you can end up with an arbitrary belt state between your two users. So what that means is that you might come in a superposition of 1, 2, 3, and a superposition of 1, 2, 3. And by the time you swap this entanglement and generate a bell state between Alice and Bob, it could be the 1, 1, 2, 2 state. It could be the 1, 1, 3, 3 state. It could be the 2, 2, 3, 3 state. So you don't get to pick what frequencies you get, but you do quite frequently end up with a 2-level bell state. The reason you get this is really just kind of an interesting math trick. But essentially, when you put one photon from this bell state into the beam splitter and one photon from this bell state into a beam splitter, and then you do the frequency demux at the output, there's only d ways that these photons end up in the same frequency and are therefore give you that undesirable double click. But most of the time, d squared minus d of the time, you end up with these photons in different frequency bands. And if you end up with them in different frequency bands, you end up with them in this particular bell state. And this particular bell state will always have a unique detection pattern. What this means is that you can generate a bell state between two users if you start with a maximally entangled high dimensional system in d dimensions with success probability d minus 1 over d. So as your system becomes arbitrarily high dimensional and arbitrarily maximally entangled in these high dimensions, your success probability of a good bell state analysis, of generating the bell state that you need, goes to 1. All right, so this is just ideas that I want to get out there, that while we might get stuck if we start limiting ourselves to, okay, what does the abstract notation say we can do? What do the actual gates let us do? If we're willing to think a little bit broader and look at the actual degree of freedom we're working with and really explore what it can do, you can overcome some limitations in what you want to do. All right, and with that kind of concludes what I want to introduce about bell state analysis. And so what I want to talk about more generally now is, what if you really just want to know exactly what quantum state you have? We're no longer assuming that you're in a bell state. Now you don't know anything about your quantum state, but you'd like to. So we're going to get to tomography on the next slide. But first, we need to introduce the most general way we talk about quantum states. I've been talking in terms of vectors this whole time, and that's not really properly general. That only applies to pure states. Okay, so imagine I have a machine that emits a photon in horizontal polarization with 50% success probability, or a photon in vertical polarization 50% of the time. Okay, this is not the same thing as emitting a photon in a superposition of H and B. Okay, that's just diagonally polarized light. All right, so the actual state we would write like this. We have to start using density matrix notation in order to indicate that there's no well-defined phase relationship between horizontal polarization and vertical polarization. Okay, our actual state is this: 50% chance of being in H, 50% chance of being in B. That's different from a state that emits in an actual superposition of H and B, which would be represented by actually this density operator, if you want to think of it in those terms. Okay, because these states are meaningfully different. For instance, this state is in H 50% of the time, and if I put it through a diagonal polarizer, it will go through the diagonal polarizer 50% of the time. All right, it's also in vertical 50% of the time. If I put that through a diagonal polarizer, it'll come out 50% of the time. So in total, if I try to measure this state with a diagonal polarizer, it'll work half of the time. If I try to measure this state with a diagonal polarizer, it works all of the time. All right, these states are in a superposition. These states are not. Okay, and then the same notation generalizes to multi-party states. So for instance, our favorite Bell state, the 0, 0 plus 1, 1, has a density matrix that looks like this. You get this just by taking this state, which is a ket, and multiplying it by its complex transpose, which is a bra. And so if you multiply a column vector by a row vector, you end up with a matrix. Okay, these are density operators. Okay, so in general, a set of n d-level qudits will be represented by a d to the n by a d to the n density matrix. Okay, so given that this is the most general framework we have to work with quantum states in, how do we measure that? How do we deal with that? It's actually quite difficult. So generally, tomography is going to require on the order of a d to the 2n unique measurements, because you have to get information about every single one of these elements in your matrix. There's some long-standing approaches like linear inversion. You say, okay, you have this state, you want to learn about it, go and make this set of measurements, tell me your results, I'll do an inversion and I'll figure out every single element of your state, and it'll be great. That does not play very well with confidence intervals. We don't make any kind of measurements for an infinite period of time. Okay, we're always going to have rounding errors and just limited data in whatever we're collecting. Linear inversion very commonly will end up with a quantum state that can't actually exist. Just because quantum states are kets times bras, they're always going to be Hermitian, positive, semi-definite. Linear inversion oftentimes ends up with states which are not those things, okay, with states that don't actually exist. Maximum likelihood is a little bit better. You do always end up with states that exist, but there are some limitations to it. It just returns to you what's the most likely state that your data represents. But it doesn't really return to you any kind of confidence interval on your state, which again is kind of inherent whenever you're making measurements like this. We have done maximum likelihood style measurements in our lab, and they're pretty difficult to do. And so we had this state, which in principle is, let's say it's 40 dimensional, but really it has maybe like 12 really good dimensions in it. We did not do quantum state tomography on this whole state. That's a heck of a lot of measurements. It's very difficult to do because all of these measurements require you to interfere the different frequency states of your photon. You have to be able to do a lot of interferometric measurements to get the required information you need for a maximum likelihood estimation. So even though we had all of these dimensions, we only looked at the essentially frequency 6 and 7 states and actually did a 2-level tomography, which was very successful. But again, it's a 2-level tomography. It was mostly done that way because it was so difficult to do any higher dimensionality in that. Okay, and then there comes in something that's a little bit more helpful, a little bit more usable, which is Bayesian tomography. If you know anything about Bayesian estimation, that's an idea that exists outside of quantum. It just says you have some kind of initial prior that you think describes your state, you gather some evidence, and then you do an iterative process to figure out what you now think your state is. So it's just an iterative updating process. And we did a Bayesian state tomography recently with a collaborator, where we put light into our microring resonator, which is what generates our high dimensional states for us photonically. And then we did a pull shaper followed by an EOM, which is kind of a new thing for us to do. Usually we would have used an EOM followed by a pull shaper followed by an EOM, because that, as we saw a few slides ago, is a quantum frequency processor. Quantum frequency processor is able to stay ideally in the computational space you're working in. If you say this frequency is state 0, this frequency is state 1, this frequency is state 2, I can do a quantum frequency processor that will stay in those states. It'll, change frequency bin 1 to a superposition of 0 and 2 or whatever, but it'll never scatter me to some state that I haven't defined. Here, we were actually doing a tomography, a Bayesian tomography, where we were willing to be scattered to other states. We were willing to go outside of the computational basis, because even though we were outside the computational basis, we could still figure out what initial state would give you those results when you drove the EOM at that frequency, when you applied that particular phase to the pull shaper. So I won't go that much into this other than to say that this requires many fewer measurements than a traditional tomography with maximum likelihood estimation. And it also, because we didn't try to confine ourselves to what we do if we're working in a really abstract framework where we were just thinking about, okay, these are the quantum gates we can do. We were willing to work outside of that basis. We're able to do reconstruction, and we did it up to 7-dimensional, high-dimensional frequency systems. All right. So we reconstructed these density matrices, and these density matrices are characteristic, if you look at these quite a bit, of states that are very, very highly entangled in many dimensions. And actually with that, I'll go on to our final topic, which is entanglement certification. So quantum state tomography is great if you want to learn about the entire state. There is a limitation with Bayesian state tomography because it's just giving you what's the most reasonable guess for this state to be. It doesn't quite work so well for certifying how good is the state as a resource, which we like to do with entanglement certification. Sometimes we really don't want to have to go through all the bother of figuring out exactly what the state is. We just want to know, what could I do with it? Can I use it to teleport states in a quantum network? Does it have enough entanglement to be useful as that kind of resource? Like, how well does it embody this fundamental property that's really interesting about quantum circuits? So really, when you're doing entanglement certification, you're trying to distinguish highly entangled states from entirely separable ones. All right, this is our famous Bell state from earlier. Okay, this is a 2-photon state that would essentially be 50% probability of HH plus 50% probability of VV, but there's no coherence between the two. All right, and there's a lot of different ways people go about trying to accomplish entanglement certification. There are a lot of different inequalities people can do, where if they violate an inequality, your system must be entangled. And if you violate it very strongly, it actually must have a significant amount of entanglement in it. So one example of that is the CGLMP inequality, which if you've heard about Bell's inequalities, they're pretty much just Bell's inequalities, but for high dimensional systems. And we actually did that in that paper I showed you before, where we did that 2-level tomography. We also did a 3-level CGLMP inequality to demonstrate that that system was entanglement that required at least 3 dimensions to realize. All right, so in this case, in order to do that kind of inequality, we did have to overlap these 2 bins and then overlap another bin on top of it. Again, these are fairly difficult measurements, which is why we didn't go any higher than qudits. All right, there's something I do want to point out here. There are a lot of measures of entanglement. So there's inequalities which show you that entanglement exists. And there's also things that are called entanglement measures. They work to quantify entanglement in some way. They work to quantify how many Bell states could I distill out of this quantum state if I needed to, or if how many Bell states are required to form this quantum state. There's also, and properties of entanglement measures, there's really 2 big features that all of them have. They always have to be 0 for separable states. So every single state that's separable has the same entanglement, which is none. That's called vanishing on separable states. And they also can't increase under LOCC operations. Okay, what we talked about a while ago, local operations, classical communications can never increase entanglement. If you have a measure that satisfies both of those, you can write a paper about it, slap your name on it, and put it out there. There are a lot of entanglement measures, but there's only a few that I think are in really strong use anymore. There is something I do want to point out, though, which is mutual information, which pops up a lot and is fairly useful, although it's not technically an entanglement measure. It has a lot more in common with an inequality, because mutual information represents how well correlated is your system. And classical systems can be correlated. For example, if I have this state, this is a correlated state. When photon A is in H, photon B is also in H. When photon A is in V, photon B is also in V. These are correlated. There's just no coherence to their correlations. So this kind of state would be maximally correlated in a classical sense. Okay, and it would actually manage to have one bit essentially of mutual information in this state. Quantum states like this one, can actually have 2 bits of mutual information in the system. So this is the most correlated a classical system can be. And so a separable state will always, for any given dimensionality, will always have mutual information under this line. Whereas entangled states can have mutual information that exceeds this line. All right, and the closer you are to being at the entangled maximum, the obviously more entangled your system is. All right, so that's just a very slight variation on most entanglement measures is mutual information, which does almost the same thing. It's just not vanishing for separable states. All right, and some work we've been doing currently in our lab uses an entanglement measure called the relative entropy of entanglement. A lot of these entanglement measures are difficult to work with because they have a really well-defined operational meaning, but it's really hard to devise a set of measurements that even tells you what your, for example, relative entropy of entanglement even is. There actually are quite a few measures, and I think relative entropy is one of them, for which if you have just the quantum state, you've done a tomography, you know everything about your quantum state, it's still awfully hard to figure out what the value of that entanglement measure is. One entanglement measure, which is famously not the case for this, is negativity. Oftentimes people use log negativity instead. But that's something that you can look at a quantum state and immediately calculate the negativity. That's not true for most entanglement measures, actually. Most entanglement measures, if you look at the quantum state, and if it's not a really ideal state, you wouldn't know what that measure is, which can be frustrating. But in any case, in our lab, some of the most recent work I've been doing is four types of states that we tend to produce in our lab, which are these highly correlated frequency states. So frequency states where photon A is in 1, photon B is in 1, photon A is in 5, photon B is in 5. That's a highly correlated state. It's not necessarily entangled. Entangled requires there to be coherence between these frequency states, which is usually really hard to measure. It just takes a lot of measurements to quantify how much coherence you have. Instead, I've been doing some work and saying, okay, we can do a bunch of easy measurements, which are just like putting these photons through demuxes and looking at coincidence counts. Okay, if this photon is in 1, is this photon also in 1? Great, that's an easy measurement to do. Combining that information with just one fairly challenging, but still not the worst measurement that you have to do, which is measuring the purity of a system state, which there are ways you could do that, even though intuitively you might not think that you could at first. We have a way of certifying a minimum amount of relative entropy of entanglement of the system. And so for more and more pure states, you can generally certify higher and higher relative entropy of entanglement. And so that's something useful to look at, because then we might be able to say, okay, we have this source that produces entangled photons, and we have this source that produces entangled photons, but which one of them is better? Which one of them would we want to pursue in some kind of like commercial application? If we have to do tomography on all of these different rings that all generate entanglement, it'll take a long time. If we have a quick, relatively painless way that scales easily for high dimensional systems, that would be our preference. And that's some of the work that I'm doing right now. And so that's kind of all I want to say right now about entanglement certification. And so in summary, today we did a lot of intro work, and then we talked about Bell-stick analysis. Why do people care about that? It's absolutely central to quantum networks and quantum communications. And we talked about quantum state tomography, just kind of self-explanatory. Sometimes you just want to know what states you're doing, especially if you're trying to validate that your quantum circuit does what you think it does. You want to put in a known quantum state. You want to have your gates operate on it. You want to completely characterize the output state so that you know that your quantum circuit gates do what you think they do. Okay, there are a lot of applications for wanting to know exactly what your state is. All right, entanglement certification. Okay, quantum states can be awfully large, all right? Sometimes we don't really need to know every single thing about them. Sometimes we just want to get information about one of their most important features, which is how much entanglement they have. So that's all I have to say for today. Thank you all for listening, and I can answer any questions.
If you have questions, you can talk about the box. So that's thanks to Annie for the talk again.